Hey guys, and welcome back to another video on the channel. In today's video we're going to be solving this partial differential equation. So x multiplied by the partial derivative of u with respect to x plus 3 of u is equal to x squared, where u is a function of x and y. Okay, so to start off with this, we're going to be using a substitution via the chain rule pretty much. So what I'm going to do is rename a couple of things. So what I'm going to say is, alright, let x equal dx dt, where t is a new parameter I'm introducing, and let 0 equal dy dt. Okay? So if I do this, I'm going to integrate with respect to x, so I'm going to move the dt up there, so dt equals dx on x. If I integrate both sides, that is a terrible integral, sorry, I'm going to get that t is equal to natural log of x plus c. Now I'm going to rearrange it to make x the subject, so x is equal to a e to the t, where a is a constant and this c is a constant. So if you don't know what I've done now, all I did was move the c over there, so I have t plus c equals natural log of x. Then I wrote it like this, x is equal to e to the t plus c, and I rewrote it like this, x is equal to ec e to the t. This is just some constant a that I labeled there. Okay, so now that I've got that out of the way, I'm going to copy my partial differential equation and insert a substitution pretty much. So I'm going to let du dt be equal to the partial derivative, well, dx dt, multiplied by the partial derivative of u with respect to x, plus dy dt, multiplied by the partial derivative of u with respect to y. Now, technically, I do have that in my differential equation here. All I have is a zero term here, pretty much, which accounts for this term here, because dy dt is 0. So technically I can replace this stuff with this stuff here. So I can rewrite that as du dt plus 3u is equal to x squared. Now what is x? X I defined as a e to the t. So now I can replace this as well in there. So I get du dt plus 3u is equal to a e to the t squared. I'm going to define a squared as another constant, let's say c, and evaluate that side there. So I get du dt plus 3u is equal to c e t squared. 2t, sorry. So now that I've got that sorted, I now have an ordinary differential equation that I need to solve. So now I need to introduce an integrating factor. So your integrating factor, multiply everything by the integral of whatever with respect to t of whatever the coefficient of this term is, which in this case is 3. So our integrating factor will be e, the integral of 3 dt, which will be 3e3t. Okay, so if I do this, I should get a perfect derivative on the left-hand side. So multiply everything by this term here. E3t du dt plus 3u e3t is equal to c e2t multiplied by e3t. So all I've done there is gone times e to the 3t on the left hand side and the right hand side of my ordinary differential equation. As you can see here, this is almost a perfect derivative. Well, it actually is. So I can actually rewrite this as the differential operator of t of u e to the 3t. Because if I were to do this using the product rule, I would get this term and this term respectively. So I can rewrite the left hand side like that, and this side here I can simplify this as c e to the 5t. Okay, now I've got something very easy to solve for. Because remember, we're trying to solve for u, where u is a function of x and y. Okay? Now, I need to integrate, what is red? I need to integrate both sides with respect to t to undo this derivative here. So I have e3t is equal to the integral of c e5t dt. Now, when I integrate this side, rather than having a constant, it needs to be a constant function with respect to the other variable. Because in our ordinary differential equation up here, we only had x, so it needs to be a function of y that is our plus c here. So u e3t plus equals, divide by the differential of this, which will be c e to the 5t on 5, and instead of a plus c, it has to be a plus a function of y, so I'll call that g of y, and that's it. So divide by e3t on both sides of the equation, so I get u of x and y is equal to, well, c e2t because of index laws on 5 plus g of y e to the negative 3t. Okay? Now, this is not done at all yet because I have a function of x and y in terms of t, which is our parameter. But we defined up here what t was. T was natural log of x plus c. So what we're going to do is take that and bring that down here now. So technically what we have here at the moment is not u of x and t. We have technically u of x of t and y of t at the moment. Okay? But if I want u of just x and y, I need to substitute this following term here, so my function is just y's and x's. So this is t, that can go there, and that can go there. So I'll have c e to the 2 times natural log of x plus some constant there, because the 2 multiply a constant will be another constant, so I'll call that c1 on 5 plus g of y, oh that's a terrible bracket, g of y e to the negative 3 natural log of x plus some constant 2. If I have e to the power of, well, actually before we do any of that, we can bring these guys to their powers in there, respectively. So if I did that, I get u of x and y is equal to c e to the natural log of x squared plus c1, all on 5 still, plus g of y e to the natural log of x to the minus 3 plus c. Now, if I have e to the log of a, the log ln is log base e, which will cancel with this term down here and just leave us with a. So when we have e to the log of x squared, that is just equal to x squared. And when we have e to the log of x to the minus 3, that's just x to the minus 3. So we can change how those terms look really quickly if I rub this out in time. We can rewrite this. U of x and y is equal to c of just bringing this stuff down the front. So we have x squared plus c1. That would be, we can still leave that, that won't be done yet. We can break this term up here really quickly. Before we do that, we can go e natural log of x squared plus c1 is the same as e to the natural log of x squared times by e to the c1. And we'll define that as another constant. So we'll have basically, for this first term, u of x and y is c of x squared times this other constant here, which I'll call q, all on 5, plus, and then here we've got the same old deal where we have, instead of x squared, this is x to the negative 3, and this is constant 2, that will be negative 3, and that will be constant 2, which I'll call capital 2q. So I'll have g of y multiplied by x to the negative 3 times by q of 2. So if I were to rewrite this whole thing, I'll go c times capital Q on 5 is b, and I'll leave that as just q2. I'll just leave as just q in this case here. So I'll define this as q1 because it's a different q. We don't know what that constant is. So that means our answer, u of x and y, is equal to b x squared plus q g of y on x cubed. And that is the solution to our partial differential equation. It is a function of x and y that only contains an x term, a function of y, and other x terms, okay? Where b and q are respective constants. If you had any questions in this video, leave something in the comments and I'll try my best to answer them. So that is the solution to this differential equation.